feedback shift register. See, the linear feedback shift register, the feedbacks that you take will decide the kind of sequence that you are going to get. Okay, maybe I will explain that here. Okay. See, here let me take a four input shift register. Suppose I had taken this guy and this guy. Let us see whether it generates. Okay, initially let us start with 0 0 0 1. Then XOR of these two will be shifted here. XOR of these two guys will be shifted here. XOR of these two guys will be shifted here. XOR of these two guys will be shifted here. Oh, sorry. Let us make sure that we are doing it right. XOR of 0 and 1 is 1, 0 0 0. XOR of 0 and 0 is 0, 1 0 0. XOR of 1 and 0 is 1, 0 1 0. XOR of 0 and 0 is 0. One zero one. XOR of 1 and 1 is 0 0 1 0. XOR of 0 and 0 is 0 0 0 1. So, you can see that it cycled back very quickly. It did not generate all the other states. Okay. So, it is a 4-bit register. So, it can have 16 possible states. From 0 0 0 0 to 1 1 1 1. See, 0 0 0 0 is not allowed because that will lock the LFSR into the same state forever. So, ideally I would like to have 2 to the power 4 minus 1 states. Okay. In general, if you have n-bit shift register, I would like 2 to the power n minus 1. Such a LFSR is known as a maximal length LFSR. Okay. Sometimes the feedback pattern, okay, here I took the feedback of these two outputs. So, we sometimes write it like this. See, this term is labeled 1, this term is labeled x, this term is labeled x square, x cube and x power 4. Okay. So, we sometimes write it as 1 plus x square plus x power 4. So, this is a way of writing the LFSR's architecture, right, in a compact way. Sometimes people call it as a characteristic polynomial. Okay. In the previous exercise, the characteristic polynomial of this is what? 1, this is x is not included, x square and x cube. So, when you see the polynomial, the degree of the polynomial will tell you how many flops there are. So, in this case it is a 3-degree polynomial. So, this must have 3 flip flops. Okay. In the same way, here the degree of the polynomial is 4. So, that means it has 4 flip flops. So, when we build an LFSR, the characteristic polynomial makes a difference. Some characteristic polynomials will lead to a maximal length LFSR and others will not. Okay. For the same degree, there may be several polynomials that will work. Okay. So, I will give you this as an exercise. So, take this LFSR, write down its characteristic polynomial, and simulate the LFSR, verify whether it is a maximal length LFSR. And same, please do the same thing for a 4 bit. See, we are allowed to take the feedback of more than one. Okay. So, in this case we have taken the feedback of this, this and this. So, that is considered okay. Maybe I should write this better. So, we take this guy, and we take this guy, and we feed it back. So, this is a 4 bit LFSR. Please simulate this also and check whether it is a maximal length LFSR. Okay. We will do this exercise in we will take a slightly bigger one, maybe we will take 5 bit LFSR. So, the characteristic polynomial is x power 5 plus x cube plus 1. Okay. So, we have 5 okay. So, we will do one thing. We will take a scan flop, because that I have already done all the things like okay, let me put a scan flop. I need 5 of them. And it is a shift register, and according to Wikipedia, it is for 5 bit LFSR it is x cube plus x. So, the parallel input will sort of use this to load it. Okay. So, we will have this will allow us to put any seed value. and usually we initialize it to 0 0 0 1, but then it is up to you. Okay, you can choose any other seed. Then because it is a serial, I mean it is a shift register, right, the output of this has to go to serial in here. The output of this has to go to serial input here. Yeah. Okay, and output of this has to go to serial in here. And the x cube, this is 1 x square is output of this x cube. So, we need to take this guy here, this is x power 4 and this is x power 5. So, there has to be an XOR gate. So, okay. The output of this has to feed back here. Okay. The scan enable is initially we will keep it 0 when we are loading the register, and then we will start to shift. So, we will keep one scan enable. Something wrong here. There is some piece of wire there. And then we have to take the Q out and connect it to serial in. Scan enable has to be connected. Scan scan enable has to be connected. Then scan enable has to be connected. And then scan enable has to be connected. Okay. Then the clock and the reset have to be connected. Frankly, in this case, reset is not entirely required because we have the ability to load it with any value we want. There's some wire here also. See, there is a short circuit here that we need to get rid of. It's terrible. Alright, now the clocks got to be connected. So introduce a clock pin, connect the clock, oh. Okay, this reset also is not fully connected. reset has not gone to this reset has gone to this. This reset has still not gone here. And then this one, let us remove. This last clock has to go here. Okay. All right. So let us all right. Oh, this came off. All right. Let us attach LEDs . So, initially the reset is high. So, let us label these guys so that we do not get confused. This is reset, this is clock. Then this guy is scan enable. So, we could also say load or shift. And these are the parallel inputs. Okay. Initially, I have put the seed as 00001. So, let us initialize oh wait, there is something wrong here. This has to go here, right? Yeah. So, initially I will keep the load or shift to 0 so that we can load it. Let us apply a clock. So, you will see that 00001 has been loaded. Okay. Now, if I now we have to go and start shifting. Okay. So, let us so you can see that the XOR caused a 1 to come here, 1 followed by all zeros. Okay. Then one more clock. So, you can see that its pattern seems to be random, right. Ultimately, it should go back to the all 00001 state. See, it has come back to the 0001. So, I believe it took 31 clock cycles to do this. Okay. So, this is an example of a linear feedback shift register. So, in this example, we took 1 plus x cube plus x power 5, right. There may be other characteristic polynomials which will also work. Okay. So, we have to, so I want you to try this exercise. Okay. So, build an LFSR build an LFSR whose characteristic polynomial is, let us take one of these guys, let us say this one, x power 8 plus x power 6, so 8, 6, 5, 4, 1. Okay. So, this is the exercise that I want you to do. Use circuitverse okay. Start with a seed of, let us say 25. Okay. Verify that this is a write down the sequence of states generated, okay, starting from 25, and how many states did you generate? Okay, before returning to state 25. Okay. So, when I say 25, I mean the number 25. Okay. So, exercise. So, yeah.